Good evening. Welcome to Lesson 11 of CE3372, Water Systems Design. And today's lesson is the last one that formally deals with EPANET, the program. There's a homework assignment that is rendering on the other computer right now and will be uploaded realistically sometime tomorrow. And also coming up will be the first exam, and that will be uploaded to Blackboard with any luck before the weekend so that you have the entire weekend to work on it. It's not that hard an exam, but I have to program it into Blackboard, and there's a high probability that I'll bugger that up at some point. So I got to program it and test it, and that takes more time than it sounds like it. It's one of the beautiful curses of modern technology is stuff that people used to be able to do fast, we can do even slower now, no matter how much we pay. Okay, so enough of my griping. Let's begin with today's show. I've already opened a connection to the EPANET server that I use for this class. Alternatively, we could go through the whole connection scheme here and we get to the same place. And in the lesson collection folder, we're on lesson 11. And if we enter the folder, we get the usual web link to lesson 11. There's a mosquito in my room. If all of a sudden I bang at the screen hard, it's because I got a shot at the mosquito that's been buzzing my head for time to die. Not quite as convincing as in Blade Runner, the first edition, but there's one less mosquito on this planet. One less live one. If it was stayed outside so a bird can eat it, it would have worked out fine for the ecosystem. As it is, I've got more mosquito parts on my floor. Okay, so let's return to the lesson. That grisly statement was actually supposed to be humorous, but it didn't come out that way. And the index page needs some work, and I'll be working on that later on. So the notes for the lesson 1 PDF, it looks like I think I already have it loaded, so I'll just go to the already loaded one. And so the topic for today is the extended period simulation part of the network hydraulic model. All the models we've demonstrated the last couple meetings are. I just realized I'm not sharing my screen. I bet somebody just told me that. Yep. Thank you, Stephen. And I got the message. It took me a while. Running slow in the brain today. And let's see, share the desktop or share the window. Let's see how this works. That should be better. Let me check the chat. Is that better for everyone? Actually showing. Yeah, okay. Got me a thumbs up. We will continue. So the extended period simulation is different from what we've demonstrated so far. So far, everything that's been demonstrated have been what are called in the software a single period simulation, or you can think of it as a hydraulic snapshot of the system, assuming that it is at some kind of hydraulic equilibrium. And that's a useful tool in and of itself, but it does not allow for convenient tracking of tanks draining and filling, and it doesn't allow us to track certain water quality features. So that's what we'll discuss today. Not if that key doesn't work. Let's try that one. So we'll examine multiple period simulation, the reasons for its use, how it's implemented in this particular program. It's done so by something called a multiplier table. and look at the tank models that are embedded. So everything we're going through today is taken from the EPANET user manual, and there's a section that's not labeled, it's not conveniently labeled this, but they discuss how to model storage tanks in a water distribution system. These two web links have absolutely nothing to do about EPANET modeling, and I don't know how they found their way into this particular slide, but I'm a little too late to remove them for the time being. Let's recall, oh, that other mosquito has got to go. I missed you again, didn't I? Yeah, so now you gotta go. I like the cooler weather, but open the windows to let air in and let the mosquitoes in too. Recall from one of our earlier meetings, either last time or the time before, probably last time, we looked at this particular problem and ran a simulation and explored different features of the network. So this is an example of a single period simulation, and in this problem what's relevant is all we did was enter the pool elevation in this tank, and at no point did the problem have any concern with whether there's enough water in that tank or not to sustain the flows that are computed. When that is a question that we want to ask, we would have to look at something called the extended period simulation method. So recalling our modeling protocol, we sketched layout on paper, pipe diameters, length, roughness values, node elevations, demands, supply reservoir, pool elevation, and pumps and pump curves. So that's the protocol that's appropriate for single period simulation. If you'll recall the way the tank in this picture is modeled, here's pipe number 8 connecting the tank to node 2. Pipe number 8 has a total length of 300 feet, and I've elected in the drawing to make the assumption that 180 of that 300 feet are running horizontal from the node at the same elevation that the node is, and then going underneath the tank and running up 120 feet in the air to the bottom of the tank. And so the tank can have water levels or pool elevations in it ranging from 300 feet to 315 feet, and I believe I supplied a tank diameter of 50 or 60 feet in diameter. So if we turn our network on, it's certainly in this case, if we examine that, hydraulically what's going to happen is this tank is going to start to drain as it supplies water to the network. And if there's no additional water brought into the system, it probably will not sustain the flow rates very long until it drains completely and there's no supply left. As previously stated, the single period simulation is not suitable to answering a question like that. That's when we resort to something called extended period simulation. EPANET and similar programs, KY Pipes being the main one I know of, and I forget what the European version, it has a name, it's not SOBEC, that's a drainage program. Well, I can't remember right now. They all work quite similar to one another. EPANET in particular finds steady flow solutions. That's all it can do as far as network hydraulics is concerned. So what the extended period simulation procedure enables is it produces a sequence of steady states, and within that sequence there's approximations provided for tanks draining and filling, and pressures at the beginning and end of a computational time interval, and to allow pump operating points to move along a pump curve. And the typical time unit for the hydraulic simulations, typically on the order of 1 hour. So each time step is an hour, so we would do hourly simulations. And that's a pretty good time step for this approximation to be reasonably valid, because a change in flow, the pressure wave it creates, will propagate through a pipeline system at about 5,000 to 6,000 feet per second. That's a mile a second. So a pipeline system that maybe spans 60 miles in any direction. Of course, those speeds change slightly as the diameters change. The point being is any change we make now, an hour from now, the system has essentially come to a new equilibrium as far as the hydraulic network behavior is concerned. It won't be at an equilibrium as far as tanks draining and filling and operating points and pumps. But pressures propagate very fast. So this is a reasonable approximation for routine operation simulation. It's not a good approximation for studying the pressure waves in sudden pump failures or sudden valve closures. EPANET's not capable of doing that. Extended period simulation is used for modeling pressures in the systems during changing demand, usually an hourly time scale, possibly as short as every 15 minutes. Any shorter than that, and one would be realistically concerned about how accurate it would be at replicating the observed phenomenon. It's used for storage tank operation and sizing. That's one of its primarily important uses. So we had another methodology for figuring out how big to make a storage tank for flow equalization. Once we size that tank by the prior method and put a replica of it into our computer program, this tool will allow us to ask the question, did I size it adequately enough for this network in that the tank never goes dry and the tank doesn't overflow? And then the last use is for when we have to do water quality simulation. So the program can approximate water quality from multiple sources. By multiple sources, you could have 2 or 3 different reservoirs connected to your network, and you could specify different source water quality in each of them, and it can keep track of how that water quality constituent propagates throughout the system over time. And some of the uses that are employed are to estimate the age of water in the system. That's important for disinfection purposes. We don't want the water at any point in the system to become so old that there's no disinfection byproduct left. Not byproduct, disinfection residual. It can be used to detect intrusions into a system. For example, reverse flows and where they're going to end up. And in the case of an intrusion, we can use that to assess the severity of the contamination, and that in turn would help us employ a strategy to isolate portions of the network, flush them, and then recharge them with usable potable water. So those are the main uses for extended period simulation. Less used but equally as valid is the extended period simulation could be coupled with automated control systems so that the model could be used to autonomously control a real water distribution system. And there are some instances in the United States where that's being done, using actually a version of the EPANET computation engine. So this rather mundane, almost silly program that you get from the internet is remarkably useful in the water distribution industry. So how is this implemented? So one way to do a sequence of steady states is it's a bunch of single period simulations, and you would simply just change the demands at each node for each different time. That is remarkably inconvenient. And so what instead EPANET does is you set an initial or a base demand, and then we use demand multipliers to produce a temporal pattern at each node. And then we set the simulation times, and the program will follow the pattern as it's generating these sequence of steady states. For the time being, you have to take it on faith that this is actually far easier than entering individual demands. I mean, visualize a network that you're operating for a client that has 5,000 nodes. You certainly don't want to, well, you're certainly not going to hand enter demands for 5,000 nodes more than once, ever. If you have to change demands at a node, you're going to want to do that programmatically. And the demand pattern is quite a bit easier. We can simply produce a demand pattern over a 24-hour interval. So that's 24 multipliers to enter. And then we can apply that pattern to every node that it's important to. And so we only have to enter 24 things once instead of 5,000 things 24 times. So that's why they choose the demand pattern approach. And we need to modify our modeling protocol. And literally all we do to modify it is to add this additional term, which is to identify demand patterns and various tank operating considerations and put them into our model. So the modeling protocol is still usable. The best way to visualize this is by an example, and we will switch to this example shortly, but let's go ahead and do the basic layout. So suppose we have this skeleton network here. On the left, we have a storage reservoir. Think of it as a big lake, and it has a pool elevation of 100 feet, and we're using a pump to push water into the network. The pump curve for this pump here on the left reservoir is shown by this tabular information, where at shutoff it will produce 200 feet of added head. At 10 cubic feet per second, it produces 190 feet of added head. At 20 cubic feet per second, 150 feet. So there's one of our pumps. On the right side of the figure, there's another reservoir. Its pool elevation is 120 feet, and it has its own pump that's pushing into the network. And this pump here has the following pump curve behavior. At shutoff, it produces 180 feet of head. At 10 cubic feet per second, 170 feet of head. And at 20 cubic feet per second, 130 feet of head. So those are the two fixed grade nodes that are available to this network. And then there are 3 storage tanks included in the network. And the elevation storage table is down here at the bottom of the drawing. And essentially it relates the pool elevation in those elevated storage tanks to the volume of water that's in storage. So if the pool elevation is 220 feet, the tank is empty. And I'm not aware of negative storage implemented by any computer program. I think when it's empty, it's empty. At 230 feet elevation, there's 40,000 cubic feet of storage. And all the way up to 260 feet of elevation, we have 250,000 cubic feet of storage, which is a sizable amount of water. So we've got 3 of these tanks connected at node 3, 6, and 8 in this network. And then we have some other pipes and nodes and typical hydraulic appurtenances common to a water distribution network. In addition to this drawing, we have information on each pipe. So pipe 1 through 27, we have the starting node and the ending node. In this particular document, it's using the symbol 0 to indicate connections to fixed grade nodes. In our EPANET model, every node has a number, and I believe by default it starts counting as 1. So these 0 nodes don't make a lot of sense for EPANET. And we're told the length of each individual pipe in feet and the diameter in 1/12 of a foot, inches, and any additional minor loss coefficients that are available depending on where the connection is. And so This would be used to construct our node arc incidence matrix. In the case of EPANET, we'll be doing it by just drawing an image on the map. In an older style, or if we were doing our own code from scratch, we'd actually use this information to create a node arc incidence matrix, like was demonstrated when we looked at the Newton-Raphson approach for solving networks. And we only briefly touched on that. That's what's going on under the hood inside these things. We also have information on each junction, its identification number, the elevation of the junction, and then the demands in gallons per minute for each junction. And here the analyst has converted gallons per minute into cubic feet per second. 1, 2, 3, 4, 5, 6. See, so more than 6, so it would have been smarter in this case to convert the pump curves into gallons per minute and proceed that way. But nevertheless, these are the base demands. And so with that information right there, we could simply do a single period simulation and could simulate the flows and pressures in the system under the conditions of all these pool elevations being at 250 feet and the pumps operating at wherever the pump curve is. And that would be a snapshot of the system momentarily. But it's not too hard to conclude that with these tanks there, they're either going to be draining into the network or, let's see, they're probably draining into the network because they're at elevation 250, and let's look at what these node elevations, they're at least 100 feet higher than the surrounding network elevation. So they're going to initially want to drain into the network. And so our next step would be this demand multiplier construction. So this graphic is taken from, I think this is from one of my Metcalf and Eddy wastewater books, but it might be from a water engineering book by Montgomery Watson Americas before they changed their name. So this is a chart that shows the variation compared to a typical winter day, and then we have an average day. So you could visualize an average day as a horizontal line passing through 100%. So average day is a artificial construct of engineers. And then we have a variation curve for the maximum day of some year. And the maximum day of some year is expressed as percents of average day. And we have it at different times, and we can break that up into a 24-hour interval. And from this curve, we can select points off the curve that correspond to each particular time of day. And so that creates a table that looks like the table on the right-hand side of the figure. So hour 1 at clock time midnight, the factor is 1, so it's taken from right there where the cursor is sitting still. Let me move it around a bit, so if you watch this video and haven't fallen asleep yet, that will draw your eye to that location. Hour 2 is clock time 1 a.m. The multiplier is reduced to 0.9, 90% of average day. Hour 3, also 0.9, and so on. And so we can construct an approximation to this entire curve. Now it doesn't take a far stretch of imagination to observe that the total volume produced on an average day is different than the total volume that would be produced on a maximum day. But for extended period simulation, we probably want to use the maximum day because that's the most that the system is going to demand from our supply. Looking at this, just looking at it, it looks like a maximum day has nearly 2 times, maybe more, area under it than the artificial average day. And then in wherever this curve is from, this particular community, Wintertime has much less variability and much less total demand. And that makes sense. And we can find curves like this for a lot of different situations and use those to construct many different demand pattern tables. Once we have that information, then we could go ahead and build our network. And we would proceed the same way as before. We build the network layout. We put in the nodes, junctions, tanks, and reservoirs first. Then we'd add the links, and then we'd go back and put the junction elevations and junction demands, and then the pipe diameters, pipe materials, pump locations, pump curves, and any valves, which we haven't even discussed yet. You can read about that in the user manual. Valves are fairly simple to implement in EPANET, and you don't really need me to show you that. Then we add the pump curves. Remember, pump curves are in Browser, Data tab, Curve tab, and then we want to add type equals pump. And then we would add storage curves. And what the storage curves do is they allow us to assign to a tank its storage properties. It's far easier than just using min depth, max depth, and diameter, because then we're no longer constrained to whatever the geometry of the tank is once we have storage curves. Again, Browser, Data, Curves, Add, Type equals Storage. And finally, we would put in any demand patterns, Browser, Patterns, Add. I suggest that when one does extended period simulation, that you have at least 2 demand patterns. One of the demand patterns is nothing but ones, so it's pretty much just a like a single period simulation, and that's because you can use that as a way of testing that you constructed the other part of the model correctly. And so any extended period simulation, before you commit to production runs of the program, there's 3 things you can do. You can run it as a single period simulation. I'll demonstrate that shortly. You can run it with a demand pattern that's nothing but ones. You won't get identical results for those 2, but usually the first 2 time steps should be really close to one another. And then you can run it with a varying demand pattern to identify if you have hydraulic features that are not sustainable. In other words, tanks drying out or running to negative pressures somewhere. And those 3 are a good starting point that you can adjust as you're adjusting your design and preparing documentation for your client that the design network will satisfy their expectations. So returning to the prior example, so here you can see there's 2 patterns provided. We'll go look at this live in a second. And then there's the network model, and the way you know you're doing an extended period simulation is when you run this simulation and it gets done, in this upper right corner of the network map on the graphical user interface, this rectangular box appears with a day and a time of day reporting interval. So it's telling you what day and time that picture represents relative to the starting simulation time. So this is day 1, 12 a.m. That's the default first time step. And then if we were to step through the different time steps, the contents of this box will change, go 1 a.m., 2 a.m., 3 a.m. And the arrows might change direction depending on whether tanks are filling or draining, and the various numbers associated with the hydraulic elements that we have instructed the computer to report to us will change. And here's what I call the constant demand pattern. Here's what a demand pattern looks like. It has these time periods, and the default, I believe, is 24, but you can add time periods almost willy-nilly. And it's showing the multiplier as 1 for all of them, and it has a drawing here, and it has an average value, and since the average value is 1, you can think of the average as the total area under this thing divided by the total number of hours. And so if we're putting a variable demand pattern and we want to try to guarantee that the total volume to the system doesn't change, we would jack around with the multipliers a little bit to try to keep this average as close to 1 as we can. There's a fair amount of trial and error doing that. It's one of the few things that's not easily predictable up front. It probably is. I just found it faster to just move multipliers around and look at the computed average, or if you will, area under this pattern. Then in data options times, we want to change this number to however many total hours we want to simulate. So in the picture right there, it's showing 24 hours. It has a hydraulic time step of 1 hour, so there's going to be 24 reported time output stamps, or stress periods, if you will. And the clock start time is set at 12 a.m., but that's changeable. And some of the other parts are irrelevant for this simulation. You can just use the defaults. And lastly, in the browser data curves, we've selected one of the storage curves. And so the storage curve has the height of water in the tank, and the description is storage tank depth above the tank bottom, and then the associated volume. And I have a notation here that says I added this point, the original problem, the tanks aren't big enough. So it must have been an issue in the original problem where the system would start to drain. So here's the case with the variable demand curve, and that pattern is identical to the one on that handwritten table back here. And the approximate area under that curve is about 1.75 times bigger than the original average. So I think what I eyeballed, I thought it was somewhere around 2, but with the numbers that I supplied, it's more like around 1.8, which I guess is somewhere around 2. So there's almost twice as much volume in this variable demand pattern. So naturally, if we wanted to match them, we could have made the trim those 1.0s into 1.76 multipliers, and then we have volumetrically comparable simulations. And the last thing, when you run it, we might produce an output report. The output report for the cases where we're using time-varying simulation has a little more information than an ordinary output report. So this, in this case, this one was run on version 2.0, so that's a few versions ago. It was run in 2010. Oh, what's the date? Literally 10 years and 2 days ago was when this simulation was run. It has the pipe IDs, the starting nodes and the ending nodes, and that's pretty much the same as was presented in the problem setup. It has the 3 storage tanks identified. It has the left and right reservoir identified, and it states here that these are connected into the system with a pump. And then when it does its reporting, it reports results by time block. So the nodal results at 0 hours are listed here. So that's the first stress period, and it's telling the demand at each node, the computed demands at the reservoirs, the computed demands at storage tanks, and then the associated head in feet, and the pressure in pounds per square inch. And in this particular case, tank number 1, 2, and 3 are actually filling. Water's going into those tanks. Then it has the link results at that same time interval, and it does on multiple pages, and I've joined them together in this graphic. And then for each of the links, it shows the flow in cubic feet per second, the associated velocity in feet per second, and then the head loss per 1,000 feet in the element. And then head loss per 1,000 feet in a pump doesn't make a lot of sense, but you can think of this minus 189 is that pump is adding 189 feet of head per 1,000 feet of equivalent pipeline at 20 cubic feet per second. So it's following its pump curve. Then it repeats for the next hour, so no results at hour 1, and so on. And then it goes to the next hour, and I've skipped a few hours, no results at hour 6. And here, the reason I've illustrated is the tanks are now starting to drain. Storage tank 2 has changed from filling to draining. The pump is now producing different flow rates and different heads to accommodate the changing hydraulic conditions. And that is pretty much the report. So let's go ahead and take a look at that live. I want to keep this screen positioned to here so I can move back and forth. So I'm now switching to the shared atomickitty.net server, and I've already loaded this example in. It's in lesson 11, and we're going to look at the L11-1.net. So the network's already built, and we can look at the underlying base map, which is, oh, that's why it didn't work so good today. That's not the same problem. Most interesting. Good, I had a complete story concocted for why it didn't work so good this morning. Okay, well, we'll see what we come up with. So the files are already there. Let's launch EPANET. And we will now open okay, so let me look at that picture and compare it to this picture. These are the same networks. So I have the wrong base map loaded. That seems to be the question. Let me make a little bit more real estate on the screen so we can see what's going on. Some of these 10-year-old models, the layout isn't quite as good as it would be if I were to build them today. But watching me move dots and stuff around on the screen is probably not the best use of collective time. Let's see, edit, select all. How do I zoom out? View, zoom to full extent. Still not working right. Boy, that's really annoying. Okay, so there I've tried to rearrange it and I get everything to fit on the screen. So here's the 3 tanks. Tank 1, Tank 2, Tank 3. Tanks, you're welcome. And the left reservoir, the right reservoir, pump number 2, pump number 1, and then the various junctions and pipes. So let's go ahead and turn on some annotations so we can see what we're looking at. So if we go to the view options, we go to notation. Hopefully that's not too big. So the various elements are now identified. So the numbers that are adjacent to a node are the node ID. And the numbers that are adjacent to a link are pipe ID. So for example, pipe number 12 is 5,500 feet long, 18-inch diameter, has a roughness of 1. So what that tells me is this is probably using Dorsey-Weisbach head loss equation, and we can confirm that. The flow units are in cubic feet per second, which is also reported down at the bottom of the user window. And we'll just pick node number 2. It's at elevation 110 feet. Its base demand is 1.54 cubic feet per second. It's currently using demand pattern 1. We can go here to the data tab, choose patterns, and we can look at demand pattern 1, which is not terribly interesting. But demand pattern 1 has 24 repetitions of the multiplier 1. So it's a sequence of 24 identical simulations. The only thing that changes between them is the head in each of these storage tanks. So let's go look at the storage tank. It's using volume curve number 3. So if we look at curves, there's a volume curve 3 right there. And if we're at the bottom of the tank, there's nothing in storage. We can go as high as 50 feet above the bottom and store up to 350,000 cubic feet of water. And I want to see what curve number 2 is, a pump curve. So that corresponds to pump number 2. Okay, so let's go to the options and we'll look at times. And I'm going to change that to a 0. So this will be a single period simulation, and we'll know that because none of this stuff here will light up. In the time window when the simulation is completed, it will say single period. I think what we want to plot at our nodes would be, we want to plot head because that will give us what the pool elevation is at the storage tanks. And for the links, we will plot their flow values. So now by turning those on, they're all NAs because they've not been computed yet. We know that because the water spigot here doesn't have any water squishing out of it. We run the simulation, and now we have water flowing out, and the red numbers in this drawing are corresponding to the head at the different nodal type elements, and the blue numbers pretty much are corresponding to the flow rates in cubic feet per second. So if we look at storage tank 1, 2, or 3, all 3 of them have water flowing into the storage tanks. So presumably the tanks are starting to fill. But we can't see anything because this is not an extended period simulation. It says so right there with a single period. In this upper right hand corner, the black time box just says that we're day 1, 12 a.m. So to run multiple periods, let's just do, actually I think I'm going to do 3 time steps. I think I can keep my head wrapped around that before we go to, yeah, 3 should work. Run that, and when we go to the map, we now have 3 time steps. So let's keep our eye on the total head, and let's, for the grins, we'll pick storage tank number 1 because it's sitting out here kind of all by its lonesome and being ignored by the rest of the network, and it needs some love. So at 0 hours, we have almost 4 cubic feet per second going into the tank. An hour later, we've dropped down to 2.6 cubic feet per second going into the tank, and the head in the tank is increased by 2.86 feet. And if we recall what that storage curve looked like, 2.86 feet at that depth is a fair amount of water in storage. We go to our second hour, we're 254 feet of depth in the tank. We're down to 2.3 cubic feet per second coming in. And at hour 3, we're down to 2 cubic feet per second, and we're at 256 feet in the tank. Let's go back to our curve and see what we are learning. Oh, darn it, I just lost. Do I still have control? I have to go ahead and exit the program that just crashed. So when that happens to you, that's the sign of crashing. And that was not the program's fault, that was me. I expected it to work a little different than it's designed to. So I'm waiting to see EPANET 2W. Gosh. 29246. No, that's top. There we go. You can actually remember the name of the program when it's running. EPANET2W.exe. Okay, and that's what I need is 28786. So we'll go through that all over again. One of the lovely vagaries of doing stuff in the cloud is when you lose control, you really lose control. It doesn't have a whole lot of recovery options in the actual software itself. But that's just going to get better with time, right? So we'll repeat all the work. See, turn on the annotations, bring things up to something that's viewable, turn on the map. We want to do head, flow, run. Okay, this case we have 24 hours, so let's keep track of the heads in the tanks. So storage tank 1 is up here at 7 hours. And I don't think it goes into a drainage phase. I think they just continue to fill. So the bottom of that tank is at elevation 220. So 220 plus 50 feet of depth is 270. We've got 2 feet of freeboard left. So we're somewhere up here on the curve. We're about 300,000 cubic feet of water in storage. And we ran through our 24-hour cycle. So if we were to run this a little longer, these tanks would fill up to the top. It has a plotting tool that will let us produce a time series plot of the head in that node. And so the thing is filling up and filling up. Okay, so that's one use of extended period simulation. Let's fuss with this problem just a touch and make it what I think would be a little more interesting. So let's look at these pumps and let's cut their power a touch. Let's run them about 90% of their usual, that's not the right one, I want to do it in the speed. We'll run it at 90% of their usual performance. So we'll run that. Okay, that was successful, and I'm going to do the other one. So this is the what if part. This is where these tools become really powerful. Run that pump at 80%. Okay, so we're going to have some negative pressures. Pump 2 can't run that slow, so we'll have to bring its speed up just a touch. See if we get by with 90%. Okay, and now if we were to look at the head in the tank curves, I'm not sure they change much. But now that tank is draining over a 24-hour interval. And let's go ahead and really give this program a test. So I'm going to simulate for 96 hours. So 24 hours is a day. 48 is 2 days. So 96 is going to be 4 days. I don't know if it will actually complete it. We might get the a pump failure error or possibly a negative pressure. All right, let's go take a look at the storage tank. See what the behavior is under these new conditions. And that tank just keeps draining and draining. Let's see if this one, I'm trying to get one that fills and drains. That one also keeps draining. I bet you this one keeps draining too. So I'm not going to fuss with it anymore, but that is an example of extended period simulation. And but if the pattern starts to change, all we would do is we just change it here. We can make a new pattern by using this symbol right there in the browser window. Actually, I think I want to do that. I'll leave this one alone. I'll create a new pattern. We'll call it pattern number 2. And it ignored me because it is a piece of junk. Good, so demand pattern 1 still exists. And edit. My bad. Let me edit this back to pattern number 1. I'll add a new pattern called pattern number 2. Pattern number 2. And then here's where we would supply multipliers. So I'm going to run a pattern that's we'll run 12 instances of 0.75. And you can see how the drawing is changing as we add information. And then I'm going to add 12 instances of 1.25. And what I'm shooting for is to keep the average at 1, but we'll see a difference in behavior. Probably not very interesting difference, but difference. And if you're on your own computer, what I'm doing is the API has functioning cut and paste, which I don't have running on the cloud version. Actually, I probably do. I don't have the network bandwidth, so I'm trying not to crash my remote computer. So there's our 24-hour pattern. Our average is now pretty close to 1, and we'll press the okie dokie button. And now all we would have to do is change the demand pattern for all the nodes. And the easiest way to do that is to somehow get the screen I'll just do it a little bit at a time. We're going to use the group hug command, and so what I'm doing is I'm drawing a polygon around all the nodes that I can capture. And then I'm going to use edit group hug, and I want to edit the demand pattern with a 2. So now these have demand pattern 2. And then I think I missed, see, did I catch that one? I did. I'll manually do the ones I didn't catch. So that has demand pattern 1. That has 2. So all I got to do is capture these 2. Group hug. Demand pattern. Put a 2. Choose OK. And we're done. And now we have a different simulation. Run it. Run was successful. Let's look at the storage tank. It looks like they're somewhat draining, but we'll go ahead and we'll pick that one and we'll look at a time series of it. And in this one we can see the behavior as the demand pattern's changing. So we're getting some filling, some draining, some filling, some draining. We can modify it. We could start this at 230 feet. So we'll start these tanks essentially empty. We'll have just a little bit of, that one's empty, and the one I can't get to. Set you to empty. And this one, I had it 1, we're going to set it to empty. So these tanks are now starting dry. Run our simulation. Let's go look at the time behavior of the tank. And so we fill it up, and now we start to get the repeating pattern. So if our goal was for this tank to not only provide flow equalization capability, but also some kind of pressure control, we see that the tank on a daily pattern is ranging between 232 feet of head and 242 feet of head repeatedly. And so this is an example of where we would have repeating behavior. And if we're to run the animator, so what the animator is going to do is present these 24 pictures back to back. And I'm going to, okay, the 96 pictures back to back. And so we can watch the animation, and we'll keep our eye on the storage tank. Remember that 220 feet for this storage tank is empty by definition. So we see it starting to fill. You keep your eye on the arrow that's connecting to it, changes direction. The tank is starting to drain, so now it's providing water to the system. The arrow is going to reverse again. Now it's filling again, and then the arrow will reverse again soon. There we go. Draining, and it repeats this process as long as we tell it to. So that's one of the main uses of extended period simulation. Let me go ahead and stop that. We'll make one more change to storage tank number 1. Let's say we're cheapskates and we decide that we want storage tank number 1. We don't want to build it as big because we can pocket the money and go down and have mint juleps somewhere. So let's create a new curve, and it's going to be a storage curve. So let's say 200,000, the other 200,000, there we go. This is going to be a funny looking tank in real life. And then okay, so this tank is considerably smaller than the other two. Choose OK. And now we'll go ahead and reassign this tank to volume curve number 4. Hopefully we don't get an error. And so now storage tank number 1 is using a different volume curve. Let's see if that smaller tank will work in our system. And it won't, and we get invalid lower or upper levels for storage tank number 1. And so let's see what the error is. Initial level is 0, so the maximum level, I believe, has to come down. Yeah, it can only go up to 30. So we'll change that. Rerun it. And now let's go ahead and take a look at the time behavior of that tank. So we're pretty close to the, actually that tank still has quite a bit of capacity. We could make it even smaller, I think. So let's go ahead and let's make it smaller. Go to curves, make our tank smaller. Changing the shape of it. Ooh, that's a big tank. There we go. Okay, so the ultimate capacity is 150,000 cubic feet of storage. Choose OK. Rerun the simulation. And now we're getting closer to the tank capacity. Remember, the top capacity is 250. So this tank could still be smaller and satisfy this system. So that's how to use the extended period simulation. And I will exit that and leave that for anyone that wants to try it later on their own. Save changes. No. Oh, there's another example already there, which I believe has the varying demand pattern that was illustrated in the presentation. If we run it, we get the usual results. So if we look at over a 24-hour period, doing pressure today. So the pressures at the nodes are here's a 75 psi, 50 here. We won't worry particularly much about the pressure at the bottom of the tank, but the actual system nodes are what we're concerned with. We have these two yellow ones, which are at 48, so we're getting kind of close to the low pressure regime for this situation. And we've color-coded it so any pressure less than 35 psi will show up as red. Again, we're not going to be particularly concerned about the tanks. But as we run the simulation, we look for red right there. We have a case at 9 hours into the simulation where the pressure at this node drops below our statutory requirement. And again, we'd use that information to help redesign or alleviate whatever that low pressure cause is. By far the easiest would be to make the pipe bigger. Just go up to an 8-inch pipe, rerun the simulation, choose the OK. Remember, at time number 9 is when bad stuff happens. So we got past time 9, 10. Ooh, but now this one's gone bad. We play the same game there. We can make that pipe bigger, make it an 8-inch, for instance. Rerun the simulation, choose the okie dokie button, and then step through the simulation looking for low pressures. And all the stuff that we're doing in the graphical user interface, we can also generate tables, which are usually faster. So both these fail at 19 hours, 20 hours, 21, 22, 23, 24. So making those pipes bigger is a possibility, or we could make this pipe bigger and try to run that and systematically make logical hydraulic changes like that and see if we can get the system to work. I'm pretty sure I'm going to get... Ooh, lucked out. Everything stayed in the yellow. So that design meets our statutory minimum pressure requirements using the Texas rules. And then if there's other issues to be explored, we can explore them. So the next use of extended period simulation is for the water quality component. So we're going to go through this really excessively quickly because you've had other aspects of this in your environmental engineering class. So EPANET models water quality using advective transport in the pipeline and decay models. So the constituents in an EPANET quality model, they move, and as time elapses, they can decay according to a couple of kinetic models. And in practice, these are used to estimate the age of water in the system, the concentration of a constituent at different locations in the network at different times, and potentially to respond to intrusions into the system. It uses a Lagrangian approach for transport and various mixing approaches in tanks. And the transport that it simulates is advection only, which is transport of dissolved or suspended material by motion of the host fluid. So if you're floating in a rubber raft in the San Marcos River, you're lucky because you're not here listening to me, the particle would be advected by the river, the San Marcos, and that's advective transport. So you're being moved because the river moves. And then if you're kicking and screaming, you might add additional motion, but that's not advection. The kicking and screaming would be kind of a Brownian motion, a type of diffusion. To simulate these, we have to know the fluid velocity field, and by velocity field, that's both the speed of the fluid and direction. Well, in pipeline hydraulics, direction is pretty much guaranteed because we built a network in the model, and velocity is directly computable from the discharge in each of the pipes and the pipe cross-sectional area. And the velocity that we compute will be the velocity of this green marker in this diagram, where the total time step here, delta t, happens to be the hydraulic residence time of this pipe segment. And so that marker appears to move at a speed that's equal to the discharge rate divided by the pipe cross-sectional area, and that speed is called the mean section velocity. And then with knowing the mean section velocity, we can apply the ideas of mass balance to keep track of the mass entering and leaving our pipe segment, shrink to a small size, and ultimately come up with the fundamental equation of advective transport, which says that the spatial variation of the product of mean section velocity and constituent concentration is equal to the rate of change of time of constituent concentration at a point in space. That can be generalized to multiple dimensions, but again, in the case of a pipeline, we know the direction. And to compute any mass fluxes, we have to determine the velocity values in the domain of interest. Again, also quite straightforward in a pipeline system. So we'll skip over this stuff. Because EPANET does all that for us. And we get to this slide. So the whole purpose of all that was to provide a visual plausibility explanation of what's meant by Lagrangian time-based approach. As simplest is just to imagine that it breaks the pipes into small elements, and then it keeps track of all the volume of water in one of those small elements as it moves through the system. And so doing that is a Lagrangian approach, and then it does the mixing only at junctions and only when we want to actually get the water quality information. The other important feature is that quality time steps are at a much shorter interval than hydraulic time steps. So the hydraulic time steps are in the order of hours. Quality time steps are 5 minutes, and that's to accommodate the short travel time that occur within pipes. When the parcels get to a node, a mixing equation is used that's depicted on this slide, and it sums all the mass coming in. So concentration in times flow rate in is all the constituent mass that's entering the node. That's divided by the total flow entering the node, and the result of that is the concentration in the node. And then any flows that are leaving the node are assigned this concentration C out and used for subsequent downstream link calculations. When we get to tanks, there's 4 main mixing models that are implemented in the program. One is completely mixed, a second is called 2-compartment mixing, a third is first in, first out, the fourth is last in, first out. The completely mixed is the one that we would commonly think of ourselves, and as mass enters the tank, it miraculously is uniformly distributed throughout the entire tank. And in your environmental engineering class, this would be called, let's see, I think there's called CFSTRs, completely mixed stirred tank reactors, something like that. They had their own acronym, and the acronym changes every 8 or 10 years so that people like me sound ignorant after a while. But a completely mixed tank. Now, this is a reasonable model for relatively small tanks or for hydraulic time steps that are comparatively long compared to transport time steps, or for large tanks that, again, the hydraulic time steps are quite a bit, are a large fraction of the hydraulic residence time of the tank. So no real tank completely mixes unless we actually build features into the tank to make that happen. Lake Allen Henry, a complete mixing model would be absurd for the lake given the size of it, but it might be appropriate for certain constituents because the complexity of trying to describe the different constituent concentrations in different parts of the lake may not justify the information that we would get from making that investigation. So complete mixing is a pretty common model for tanks. 2-compartment mixing breaks it into 2 parts. There's an inlet-outlet zone that the analyst prescribes, and then the main zone, and we get a complete mixing, if you will, in the inlet-outlet zone, and then once its capacity is satisfied, then it spills over into the main zone at whatever that concentration is. And then as the inlet-outlet zone is depleted, the main zone supplies back into the inlet-outlet zone. I don't have a good mental or analogous situation of when this is a good mixing model, but it is provided in the software. First in, first out mixing is where the tank is behaving like a flow-through plug flow reactor. So the material that enters in one end of the tank exits the other end, and this material has to transit the tank before it gets back out. That is a reasonable model of water quality storage in relatively large tanks where the inlet and the outlet are physically displaced from one another. And then there's the last in, first out mixing, and this is a model of good visualization, as is you're adding layers of water to the tank from the bottom up, and then as you're draining it, they leave from the bottom up. So the bottommost layer leaves first. It happened to also be the one that just came in. The second bottommost layer leaves second, and it's the second to the most recent that came in, and so on. And this is a good mixing model to use when you're convinced that there's stratified flow behavior in the tank. So these are somewhat advanced concepts that I'll leave for you all to read on your own in the user manual and do some internet research. But by far, the common one is complete mixing, and this would be the one that I would select when I was just trying to get a model up and running, functioning. I wouldn't worry about the intricate details of some of these other things until I had the hydraulics working more or less correctly in the complete mixing model. There's also reactions that are provided for in the program. There's bulk reactions, so you can think of that as reactions that occur out in the fluid phase. And wall reactions, those are reactions that occur at the pipe wall liquid interface. And in the computer program, there are provisions for each, or you can turn one or the other off. Clearly, well, maybe not clearly. In my mind, if you're going to have wall reactions, then you would be somewhat obligated to include bulk fluid reactions. But if you turn wall reactions off, that's still fine. You can still have bulk fluid reactions. It wouldn't make a whole lot of sense to me to have no reaction in the bulk fluid and to have activated reactions at the walls. I can't envision a situation where that would be an appropriate modeling context to use, but I don't know everything. So the bulk reactions, there are 4 different reaction models that are provided for. One is first order decay. Second one is first order saturation growth. The third is zero order kinetics. The fourth is no reaction. No reaction is literally a tracer simulation. So if you want to put a constituent into your model to trace flow through the system, and certainly not through a 5-pipe system, but if you have 5,000 pipes and you want to know how constituents work their way through the system, a tracer is an appropriate model, and you would just turn the reaction terms off. And zero order kinetics is a tool for estimating the age of the water. And then first order saturation growth is a lot like the McCallis-Menton relationship that you had in environmental engineering. I think they are variants of one another. And then first order decay is very much like radioactive decay that you would have had back in your physics class. The 4 different models are listed here as this reaction term, and by choice of the reaction coefficient and the exponent, you're choosing different parameters of the reaction kinetics. Wall reactions are handled in a similar fashion, and generally they include a secondary reaction term based on location in the network. Again, that's something that's deferred to user manual reading. And as a quick example, here is a very simple network, and we're going to introduce 10 milligrams per liter of a constituent here, assuming it has a first order decay mass transfer coefficient of -5. What are the equilibrium residuals at different points in the network? And if we run that simulation, it starts out looking like this. And we would turn on the reaction terms, parameterize it, simulate it again. In this case, we're running 24 hours. And establish a source water quality in this tank. And finally, I'll let the thing run for a while, and we now have the water quality at each of the nodes. And you run the model until these numbers stop changing, and you then have an equilibrium approximation to the disinfection in the system. We can use tracers to do water age. There's a good example in the user manual on using water age. And we actually can plot the feature called age and find out that in our particular model, the age of the water at this node is 4.22 hours. So the water age is always expressed as multiples of the hydraulic time step. So our next class meeting, we will start open channel flow and leave the pressurized pipe network. As I said at the beginning, there's a homework assignment that involves EPANET. A part of the assignment is the Somewhere USA subdivision that we're working on for the semester project. And with that, I will end the phone call and wish you all a great evening. And I will see you on Thursday. I will stall a little bit while I shut everything down in case there are questions. And close that. I will log off this server. Close that. Close that. We're back at Blackboard, and I will end the call. Have a good evening, everybody. Goodbye. And thank you for reminding me to share the screen, whoever did that.